Let's go ahead and get started. Today we're going to finish up on binary trees. Last time we talked about, well, binary trees in general, which is a tree-like structure where you have a root that points to the root node. And in computer science, we like to have it start at the top and grow down, which is kind of the inverse of what a tree does, but that's okay. So the root node's on top, and in a binary tree, every node can have up to 2 children, hence binary. Then we talked about what a binary search tree, which was a binary tree with the added property that every node to the left of it has to be less than, and every node to the right has to be greater than. There are other types of binary trees, but we're talking about binary search trees right now because that, in general, is the most common one that's used. Okay, and what does anyone remember some properties of the binary search tree that we like? What's the word? That are desirable compared to a linked list or an array? Or better question, why would we use a binary search tree over a linked list or an array? I know it's Monday.
Time to search through it is log event.
Log event, okay. But a sorted array would be that way. Not that you're wrong, but that is one. That's true. So that would be an advantage over a linked list because you can't really do log event searching on a linked list unless you have some special skipped list, but we're not going to go into that. We're just going to assume not to make lives easy. So then why would we use a binary search tree over an array?
So the sorting, because it's automatically sorted, and is that cheaper?
Okay, you're on the right track. The sorting, it's automatically sorted, but it's being sorted as it's being built. But can't you do that with an array as well?
But it's not like guaranteed, right?
Well, you could put things in the correct location of the array and shift everything down, right? But what's the problem with that?
You can run out of memory.
You can run out of memory. Of course, you can run out of memory here.
But you have to actually declare the array.
Right. So yeah, you'd have to recreate the array. You said it's expensive. So what's the big O of inserting in worst case on an array? Actually, no, it's not even worst case. It's average case. Sorted, keeping the array sorted and inserting. Since you have to shift everything down, or down, that'd be your direction.
It would be O of N.
O of N, and inserting in a binary search tree on average.
Log event.
Log of it, okay, there we go. Yeah. So if we're searching, inserting, and as we'll see today, removing, binary search tree on average is log of N, which is better than the other two data structures that we've gone through. We did talk about, though, that in a binary search tree, it can degenerate into effectively a linked list, where if you add everything in order or in descending order, just one order or the other, then it's effectively a linked list with extra pointers sticking out for no good reason. But we're assuming for now that that's not going to happen, and we're just going to stick with the average case. Okay, great. We talked about that, talked about insert. So delete. All right, how do we delete? Quick, go.
You would have to find and delete the node I would want to delete first.
All right, all right.
And then you change the pointers, right?
Nice. See how simple that is? See, that's all you got to do, right? You just change the point, delete, change pointers. What more do you need, right? What else? All right. All right, let's go through this. What if we want to delete the 45?
That's easy. Replace it with null. Like replace the.
And don't forget to delete the node, okay?
Yeah, delete the node and replace it with null.
Okay, great. All right, so instead of deleting the 45, what if we wanted to delete the 48?
Save it to a temp pointer, delete it, move 40 right to 45.
Move 45 up, right? I think that's what you're saying.
Move the 40 pointer to the 45.
Right. So what he's saying here is Now have a temp pointer going to 48, then take 40 and have it point to the 45, delete the 48. Do y'all see how that's still a binary search tree? All right. Now, well, instead of deleting the 48, what if we wanted to delete the 40?
Basically same, except 35 to 48 are going to be nodes reduced instead of 40 to 45.
So the 35, I couldn't quite hear everything. What would the 35 point to?
35 would point to 48.
Point to 48, yeah. So it's basically the same thing in this situation. Create a temp pointer to 40, and have 45, its right point to 48, and then delete 40. Okay, great.
Now for the hard one.
Yeah, how do we delete 50? I did it in this order though because it does actually make things easier.
We change its value to null.
What's that?
We change its value to null.
We change its value to null. Okay, so that would still make it a binary search tree, but did we lose any data?
I check to see which data is,
That's me.
like which child from the 50 is greater
Oh.
than it, then switch.
Let's see.
All right, there's two ways to do it. I'm going to do it the hard way first because I think it'll help you see. If the 50 is being removed, what is the largest number on the lower side?
49. Wait, you're 50 feet?
That's 48.
Oh, yeah.
All right. So this 48, could it go up here and everything on the left be less than it? Well, yes, because that's why we chose largest. Do we know how to delete the 48? Yes. So let's store 48 to the side, delete 48, and then copy 48 into 50. Oh. Ah. If you piece this all together slowly, the hardest part becomes easy because you can delete everything else. That's what's important. Okay. Well, if you followed all that, we're going to do it again. But deletion has effectively 4 cases. The node to be deleted is a leaf. That's the easy one. The node to be deleted has no left subtree. That's slightly harder. And then the node to be deleted has no right subtree. Those are effectively the same, but you take them separately because the code's a little different. And then the 4th one is the hardest, or the most difficult, I should say. The node to be deleted has non-empty left and right subtrees. Must find the node containing the item, if any, to be deleted, then delete the node. Oh boy. All right, hey, let's go see if we can code something. That's not what I meant to do. Let's go into class code. Oh, we already have remove. That's great. I don't know why I did that, but I did. I think it's because of the sound effect. It's so mesmerizing. There we go. Do we have remove? All right. Okay. So we have remove. And now, what do we have in test? Oh, we're just going to do good old breadth. No, there's BT test. Perfect. You void test delete. All right. Put a space there. Okay. I wonder if I can build this tree. Let's see. If we add 60, 50, 70, yeah, as long as we add it from left and right going down, it'll work. We're at 60 and 70. And we have 30, 53, 80. All right. 30, 53, 80. Perfect. And what do we have? 35, 57, 75. $35, 57. What was the other one? 75? Yeah, 75. You'll see I'm just adding them like this.
Yeah.
Yeah. 32, 40, and 77. Okay. 32, 40, 77. And then there was actually a, okay, then 48, then 45. 48, 45. Hey, look at that. And let's see, contains, should contain 45. And then if we should do test assert bt.remove on 45 should be true. And then if we do a contains on 45, it should be false. And then we do want to do a couple of sanity checks, just to make sure we're not deleting the whole tree. Make sure 48's there and 57 is there as well. Okay. Made a new tab, by the way, down here. Number 14, binary tree, make BT test. Probably should call the function. Fail! Perfect. Line 61. See if that's the one we want. Yep, because it doesn't actually remove it because we have not implemented the remove function. All right. All right. Whew. Y'all got this. What do we do? Whew. Back up. What do we want? We're trying to remove the 45. What do we first need to do? We need, I'm sorry?
Find where the 45 is.
Correct, find where the 45 is. Although we don't need just the 45, because we get to the 45 and we delete ourselves, we're going to have a dangling pointer because the 48 is going to be pointing to something that's not there anymore, that had been deallocated. You're on the right track, I'm saying. So we need not just find 45, but we need to find
It's paired.
its parent. All right.
Do you have the nodes like have a parent pointer?
That would go against the binary search tree paradigm. I mean, we could set that up. Let's not do that. Yeah, I can see how in this situation it seemed like it'd be very advantageous because you're thinking of it iteratively. But, well, actually, you could do this iteratively as well, actually. But in the binary search tree, there really is not a need in general to do that. Yeah. So, what's another solution?
I'd be willing to bet it has something to do with recursion.
We could do either way. Either way is fine.
So you basically just have to do like a find, but until one of the pointers, the left or right pointers, is 45.
Right, and then you'd have the parent, and then you'd have the child. Yeah. All right. So how do we want to do that? We can do it iteratively or recursively.
I'm just gonna copy that code up there.
All right.
For the contains function. I don't know how Vim works though.
Let's see, contains. Oh, here we go. Well, all right. Oops. Oh, you did. Oh, nice. You're doing visual.
very badly.
It's okay. Hold on a second. Let me help you out real fast, because we do need to set up the recursive call. Right? Right, sorry. We need to set up the recursive call. So and then we'll do, instead of that, we'll return, remove. Ooh, I made it a rectangle. Sweet. All right. Return false. Node is val, return true. Well, we don't want to quite do that. Oh, well that actually, let me leave that in there, let y'all think about it. And then there was, what was it? Well, I don't know if copying this is really going to help. I think it's going to make cause more confusion. But there we go. At least we've set up the recursive call. So when you copy code over, don't just copy it and hit go. You're going to be very, very sad, because that's what we just did, and I'll show you why. First off, is node is null, return false. I'll show you why in a moment. First off, start reading the code. Parts, you copy it because parts of it are going to make a lot of sense, and other parts are not. So the first off, if node is equal to no, return false. Does that make sense? Yeah, that makes sense. All right. What about this next line? If node is val, return true. No. Should node's val equal val ever be true?
No. If we do,
No.
yeah, if we do like, see the left and right pointer is valid.
Then that shouldn't happen. Yeah, right.
Okay.
So,
What was it? Left?
I don't remember. Yeah, it's just left. There we go. If left is equal to val,
Oh, right.
yeah, no. Node left val. Perfect. So if the node,
It's null though.
oh, left is null. Oh yeah, we gotta check that. Here, I'll
Let's do it.
go ahead. Yeah, perfect. Right. So that pointer has to be valid.
Then we gotta return
Well, we're right now just returning whether we removed it or not. So yeah, return true. That's technically correct. Okay. And then let me help you out real fast with the formatting. Here we go. All right. So if it's null, get out of there. If we found it, if the left child is me, we're good. If the right child is me, we're good. Otherwise, we're going to start recursing down the binary tree. Okay, let's save that real quick and run it. So beforehand, we were failing on line 61. Let's see what happens now. So line 62. Hey, look, we made progress. Why? Because we returned true that we found it, but we didn't actually remove it. But at least we passed this part of the test case to confirm that we did find it. Bless you. All right. Now we need to actually delete it. Great. Well, we're doing this one case at a time. So right now, let's just assume that the only case that happens is the easy case where this is a leaf. Okay, let's just assume that that's what's happening to make our lives easier. So, we're going to assume that no dash left here is a leaf. How do we delete it?
So you just do, delete,
Left.
delete. And
Change the
then
pointer to node.
Yeah.
Yeah. Go, go, go. Oh boy. BT space star temp, or BT node, sorry, space star temp. There we go. Temp. Node dash left. What may be easier, instead of calling it temp, what I like to call it. There. You're going to delete this thing. Sometimes I've done delete me as well, but it is helpful to call it call it what you meant to mean to do with it. Right. So you're going to want to delete it, and then okay. Node dash left. Okay, great. See what that does. Hey, we passed. Well, those must be some pretty awful test cases. So I'm going to do this. I'm going to call it delete one left. And what the one is signifying is this one right here. And so it's deleting on the left. Perfect. So let's go down here. One left. All right, so that's there. And now let's see if we can figure out how to make it delete on the right. That'd be the 77, wouldn't it? Right? Excellent. And we should do a quick check on 75 and 80. All right. And now we failed line 88. Perfect, because we returned true that we found it, but we didn't actually delete it. Okay, y'all got this. Okay. Seemed fairly straightforward. Let's do it. Oh, well, good. All right. I'm going to pause the recording for a moment.